Military history is filled with vehicles that looked terrifying to the enemy, but far fewer are remembered for the fear they inspired in the engineers who designed them. This script examines 15 military vehicles that pushed technology so far that their creators began to question whether they had gone too far. These machines were not simply flawed or unsuccessful. They were dangerous by design, built around extreme ideas that strained materials, physics, and human limits. From tanks powered by jet engines and vehicles carrying nuclear reactors, to machines so large they could not be protected, or so fast they destroyed themselves, each example reveals the hidden cost of innovation. Together, they show that in military engineering, the line between breakthrough and catastrophe is often frighteningly thin. M1A1. Abrams with early turbine testing, firepower wrapped around a jet engine. The M1A1. Abrams is widely regarded as one of the most successful main battle tanks ever fielded. Yet, during its early turbine testing phase, it was a vehicle that genuinely alarmed its own engineers. The decision to power a heavily armored tank with a gas turbine engine introduced extreme heat, fuel demand, and operational hazards that challenged long-standing assumptions about armored vehicle design. In the 1970s, U.S. engineers selected the Lycoming AGT-1500 gas turbine to give the Abrams superior acceleration, cold weather starting, and high power-to-weight performance. On test ranges, however, the tank behaved less like a traditional diesel-powered vehicle and more like a jet engine mounted inside a steel hull. Early trials revealed that this choice came with serious consequences. Heat was the most immediate concern. The turbine produced exhaust temperatures high enough to ignite dry vegetation, scorch pavement, and damage equipment positioned behind the tank. Engineers documented incidents where asphalt softened and fires started during routine maneuvers. The rear of the Abrams became a hazardous zone, forcing crews and designers to rethink how infantry and support vehicles could safely operate nearby. Fuel consumption caused equal anxiety. Early Abrams prototypes burned fuel at an alarming rate, even while stationary. Engineers feared that a tank requiring constant refueling would place unsustainable strain on supply lines, particularly in high-tempo operations. During testing, tanks could drain reserves rapidly, reinforcing concerns that battlefield endurance would be limited by logistics rather than combat damage. Mechanical reliability also troubled designers. Gas turbines are sensitive to dust and fine debris, and early filtration systems struggled in desert conditions. Sand ingestion damaged turbine components and increased maintenance demands, raising doubts about survivability in the very environments where tanks were most likely to be deployed. Engineers worried that engine wear would sideline vehicles faster than enemy fire. Fire risk inside the engine compartment added another layer of fear. The turbine's operating temperatures meant that any fuel or oil leak could escalate quickly. Although the Abrams incorporated fire suppression systems, early testers understood that a turbine fire could develop faster and more violently than those in diesel engines. Noise and infrared signature further unsettled planners. The turbine's high-pitched whine was distinctive and difficult to mask, while its heat output made the tank highly visible to infrared sensors. Engineers feared that these characteristics would make the Abrams easier to detect and target. Test crews respected the tank's power, but found it unforgiving. Rapid acceleration and immediate throttle response punished mistakes and placed heavy stress on drivetrains and suspensions. Only disciplined operation kept the machine under control. With improved filtration, refined engine management, and revised logistics doctrine, the Abrams matured into a formidable weapon. Yet, during early turbine testing, it was a reminder that innovation can be as dangerous to its creators as to its enemies. Soviet KV-2 heavy tank, a turret too tall to survive combat. The Soviet KV-2 heavy tank was one of the most intimidating armored vehicles ever placed on a battlefield. Yet, it was also one that deeply unnerved its own designers and crews. Built around an enormous turret housing a naval-grade howitzer, The KV-2 represented an extreme solution to a specific problem. In practice, that solution created a vehicle whose sheer size and instability made survival in combat highly questionable. The KV-2 was developed in 1939 to counter fortified positions encountered during the Winter War against Finland. Soviet engineers mounted a 152mm howitzer onto the already heavy KV-1 chassis, resulting in a tank designed to demolish bunkers at close range. The weapon was devastating, but accommodating it required a massive, box-like turret that towered above the hull. From the outset, engineers worried about balance, stress, and structural limits. The most critical flaw was the turret's height and weight. The KV-2's turret raised the vehicle's center of gravity to dangerous levels. On uneven ground, side slopes, or rubble-strewn terrain, crews feared rollover. Sharp turns or sudden stops placed enormous strain on the suspension and transmission, which were already operating near their limits. Engineers recorded frequent mechanical failures during testing, confirming that the chassis was barely capable of supporting the turret's mass. Combat operation magnified these risks. The turret traverse mechanism was slow, electrically unreliable, and often jammed unless the tank was perfectly level. On even slight inclines, crews found that the turret could not rotate at all. This effectively locked the gun in place, forcing the entire tank to maneuver just to aim. In the chaos of battle, this limitation was terrifying, leaving the vehicle unable to respond quickly to threats. Reloading the main gun was another source of anxiety. The 152mm ammunition was enormous, requiring multiple crew members to handle each round. Reload times were extremely long, often exceeding 30 seconds under ideal conditions. During this window, the tank was defenseless. Engineers knew that once the KV-2 fired, it became a slow, conspicuous target waiting helplessly for the next shot. The vehicle's silhouette compounded every problem. The towering turret made the KV too visible from great distances, nullifying any hope of concealment. Enemy gunners quickly learned that while the tank was heavily armored, its size made it easy to target. Once immobilized by mechanical failure or track damage, the KV-2 was nearly impossible to recover or repair under fire. Crews respected the tank's firepower but feared its limitations. Many reported feeling like they were operating a moving artillery piece rather than a tank, aware that mobility and flexibility, core principles of armored warfare, had been sacrificed. The KV-2 stands as a lesson in overspecialization. It delivered extraordinary destructive power, but at the cost of balance, reliability, and survivability. Its turret was not just too tall for combat effectiveness. It embodied a design choice that even its creators recognized as dangerously close to the edge. Panzer VIII, Maus, armor, so heavy it could barely move. The Panzer VIII Maus was the heaviest armored fighting vehicle ever constructed, a tank so extreme that it alarmed even the engineers assigned to make it functional. Conceived in Nazi Germany during the later years of World War II, the Maus embodied the belief that absolute protection could be achieved through armor alone. In reality, that armor pushed the vehicle beyond the limits of practical engineering. Development began in 1942 under Ferdinand Porsche, when German leadership demanded super-heavy breakthrough weapons to counter Allied numbers. The Maus was envisioned as an unstoppable mobile fortress. Its frontal armor reached roughly 240 millimeters, side armor exceeded 180 millimeters, and its massive turret carried a 128 millimeter main gun paired with a 75 millimeter coaxial cannon. No Allied tank weapon could reliably penetrate it from the front. This protection came at an extraordinary cost. Fully loaded, the Maus weighed approximately 188 metric tons. Engineers quickly realized no conventional drivetrain could move such mass. To compensate, a hybrid electric system was adopted, using a gasoline engine to power generators that fed electric motors in the tracks. While innovative, the system was complex, inefficient, and fragile under combat stress. Mobility trials terrified designers. On level ground, the mouse struggled to exceed walking speed, and on soft soil or slopes it often became immobilized. Ground pressure was immense, causing the tank to sink into mud and damage road surfaces. Engineers knew that, once stuck, recovery would be impossible. No existing recovery vehicle could tow it, and field repairs under fire were unrealistic. Infrastructure created another crisis. The mouse was too heavy to cross most European bridges. Designers proposed underwater river crossings using a snorkel, with electrical power supplied by cables from another mouse on shore. This solution required perfect conditions and coordination, assumptions that collapsed in real combat. Mechanical stress affected every component. Suspension parts, bearings, tracks, and final drives operated continuously at material limits. The turret's extreme weight slowed traverse and risked jamming if damaged or misaligned. Engineers feared the tank would disable itself through mechanical failure before encountering enemy forces. Logistical demands were equally severe. Fuel consumption was enormous. Transport by rail was nearly impossible, and maintenance required specialized facilities Germany no longer possessed. By 1944, even its creators recognized the mouse had no viable battlefield role. Only 2 prototypes were completed. Neither fought in combat. The Panzer VIII mouse proved that armor without mobility is paralysis, a truth its engineers understood. Churchill AVRE, early prototype, explosives carried on a live battlefield. The early Churchill AVRE prototype was one of the most unsettling armored vehicles ever issued to combat engineers, not because it lacked protection, but because it deliberately carried massive demolition explosives into active combat zones. Designed to breach fortifications during the World War II, it turned its own crew into mobile bomb handlers operating under fire. The AVRE was based on the Churchill infantry tank, chosen for its thick armor and ability to crawl forward under heavy fire. Engineers replaced the main gun with a 290mm spigot mortar known as the petard, intended to fire a huge demolition charge nicknamed the Flying Dustbin. Each projectile weighed roughly 40 pounds and was capable of collapsing concrete bunkers with a single hit. The danger lay in how the weapon was loaded. Early AVRE designs required a crewman to open a hatch and partially expose himself to load the petard round directly into the mortar from outside the turret. This had to be done while the tank was often within enemy small arms, machine gun, or artillery range. Engineers understood that a single bullet or fragment striking the exposed charge could detonate it instantly. Even when under armor, the risk remained extreme. The demolition charge contained a massive amount of high explosive stored inside the vehicle. Penetration by anti-tank weapons or even internal fire threatened catastrophic detonation. Unlike conventional ammunition, these charges were not designed to burn gradually. They were meant to explode violently on impact. Handling procedures terrified crews. The petard round had to be manhandled into position, and misalignment could jam the mortar. A jammed round meant a live explosive was trapped inches from the crew compartment with no safe way to remove it under fire. Engineers feared that even rough terrain movement could cause accidental detonation. The vehicle's short firing range worsened the danger. To hit a target accurately, the AVRE often had to approach within a few dozen meters of enemy fortifications. This placed the tank squarely inside defensive fire zones while carrying its own demolition device at the front of the turret. Despite these risks, early AVREs were rushed into service because nothing else could breach reinforced defenses as effectively. Crews accepted the danger, knowing the mission demanded it. Later, modifications improved loading safety and internal stowage, but the core risk never disappeared. The early Churchill AVRE frightened its own engineers by turning armor into a moving demolition charge. T-14 Armata prototype, automation without a proven safety net. The T-14 Armata prototype is one of the most ambitious armored vehicles ever designed, and also one that deeply unsettled its own engineers. Introduced by Russia in the 2000s and 10s, the Armata attempted to redefine tank warfare through heavy automation, digital control, and a radically new crew layout. In doing so, it placed unprecedented trust in electronic systems that had never been proven under sustained battlefield conditions. At the heart of the design is an unmanned turret. All crew members are seated inside an armored capsule in the hull, while the gun, autoloader, and targeting systems operate remotely. On paper, this dramatically improves crew survivability. In practice, it meant that every combat function depended entirely on sensors, computers, and actuators. Engineers feared that a single electronic failure could leave the tank blind, unable to fire, or unable to respond to threats. Early testing reinforced those concerns. Fire control software required constant calibration, and glitches occasionally caused targeting delays or loss of situational awareness. Unlike mechanical systems, digital components offered no physical feedback. Crews could not feel jams or misalignments, and a frozen display or failed sensor provided no immediate workaround. If systems failed, the crew had no direct way to intervene. The autoloader created additional anxiety. Large caliber ammunition was handled automatically inside the unmanned turret. Engineers understood that a malfunction could trap live rounds above the crew compartment with no safe method for manual correction. A damaged autoloader during combat raised fears of catastrophic internal hazards that could not be addressed in real time. Mobility systems also worried designers. The Armata relied heavily on electronic engine and transmission management. During early trials, reliability issues caused unexpected shutdowns and breakdowns. Engineers feared that software-induced failures could immobilize the tank suddenly, turning advanced technology into a liability under fire. Situational awareness depended almost entirely on external cameras feeding digital displays. Traditional tanks allowed commanders to use mechanical periscopes or open hatches in emergencies. In the T-14, damage to cameras meant instant loss of vision. Test crews reported concerns about latency, image distortion, and vulnerability to blast damage. Engineers were equally concerned about resilience against electronic warfare. Heavy reliance on internal networks raised questions about jamming, electromagnetic interference, and battle damage. Unlike older tanks that could operate in degraded states, the Armata had little redundancy once systems failed. The T-14 Armata prototype terrified its own engineers not because it lacked capability, but because it represented a leap taken without historical reassurance. It asked software to replace instinct, automation to replace manual control, and digital systems to replace mechanical certainty. Until fully proven in combat, it remained a machine that embodied both the future of armored warfare and the fear of trusting it too much. M551 Sheridan, lightweight armor with heavy recoil. The M551 Sheridan was one of the most controversial armored vehicles ever fielded by the United States, and it was a design that unsettled its own engineers from the beginning. Developed during the Cold War and standardized in 1966, the Sheridan was intended to give U.S. Army airborne and air cavalry units a tank that could be air transported, parachute dropped, and still deliver heavy firepower. Meeting all three requirements forced engineering compromises that pushed the vehicle close to its limits. The program originated in the late 1950s under the Armored Reconnaissance/Airborne Assault Vehicle concept. Final production was handled by General Motors Defense Division, with strict weight limits imposed so the tank could be carried by C-130 transport aircraft. To meet these limits, engineers adopted aluminum alloy armor instead of steel. While this reduced weight significantly, it also caused serious concern. The Sheridan's armor could be penetrated by 14.5mm heavy machine gun fire and most anti-tank weapons. Engineers understood that survivability relied almost entirely on mobility and avoidance rather than protection. Firepower created even greater anxiety. The Sheridan was armed with the 152mm M81 gun launcher. designed to fire both high-explosive rounds and the M551 Sheridan anti-tank guided missile. Mounting such a large weapon on a lightweight chassis proved problematic. Recoil testing revealed violent rocking after each shot, placing extreme stress on the suspension, turret ring, and internal mounts. Engineers documented accelerated wear and structural fatigue, raising fears that sustained firing could disable the vehicle without enemy action. Ammunition design added another layer of risk. Conventional rounds used combustible casings that were highly sensitive to moisture and damage. In humid environments, especially during later combat use, these casings degraded quickly. Misfires, hang fires, and incomplete combustion were reported, sometimes leaving burning propellant inside the fighting compartment. Engineers recognized that an internal fire posed a deadly threat to the crew, even if the vehicle was not penetrated. The missile system itself caused persistent problems. The Sheridan relied on 1960s-era electronics that were vulnerable to vibration, dust, and humidity. Testing throughout the late 1960s showed inconsistent reliability, and by the early 1970s, the U.S. Army acknowledged serious performance issues. Engineers feared the system would fail under combat stress, negating the Sheridan's theoretical advantage against enemy tanks. Combat deployment in Vietnam beginning in 1969 confirmed many of these concerns. Mines and improvised explosive devices devastated the aluminum hull, often destroying the vehicle outright. Engineers reviewing battlefield reports saw their worst fears realized. The Sheridan carried heavy firepower, but its lightweight design made survival uncertain. B.1000 tank, speed that turned into mechanical suicide. The Soviet BT-7 was one of the fastest tanks of its era, and that speed was precisely what terrified the engineers who designed and tested it. Introduced into Red Army service in 1935, the BT-7 was the final and most advanced version of the BT series, derived from the American Christie suspension concept licensed from J. Walter Christie in the early 1930s. Soviet designers pursued extreme mobility, believing speed could replace armor on the modern battlefield. In practice, that philosophy pushed the vehicle into a zone where mechanical failure was almost inevitable. The BT-7 was capable of reaching approximately 72 km per hour on tracks and over 85 km per hour when running on wheels alone, an extraordinary figure for the 1930s. To achieve this, engineers minimized armor thickness, with frontal protection often no more than 22 millimeters. While this made the tank light and fast, it offered little resistance to anti-tank guns or even heavy machine gun fire. Survivability depended entirely on not being hit, a premise that deeply worried its designers. The drive system was the core source of fear. The BT-7 could operate either on tracks or wheels, requiring a complex transmission and suspension layout. At high speeds, the Christie suspension absorbed enormous forces, rapidly wearing out springs, bearings, and road wheels. Engineers documented frequent suspension failures during trials, especially when tanks were driven aggressively as doctrine encouraged. At full speed, a single mechanical failure could cause loss of control or catastrophic breakdown. The engine introduced even greater danger. Early BT-7 variants used the M17T gasoline engine, a Soviet copy of the German BMW 6 aircraft engine. While powerful, it was highly flammable. Fuel leaks, overheating, and engine fires were common. Engineers knew that a penetrating hit or mechanical failure could ignite the engine instantly, turning the tank into a rolling inferno. Crew survival in such incidents was unlikely. High-speed operation amplified every weakness. Gearboxes shattered under load. Tracks were thrown during sharp turns, and braking systems struggled to slow the tank safely. Crews were encouraged to exploit speed, but engineers feared that doctrine itself was accelerating mechanical suicide. Tanks often arrived at exercises already worn down by road marches conducted at unsafe speeds. Combat in 1941 confirmed these fears. During the German invasion of the Soviet Union, Hundreds of BT-7s were abandoned, not because they were destroyed by enemy fire, but because they broke down en route to battle. Engineers watching after-action reports understood the reality. The BT-7's speed had outpaced its mechanical reliability. The BT-7 stands as a warning from the early days of armored warfare. Speed alone could not compensate for fragile engineering. In chasing velocity, its designers created a tank that consumed itself long before the enemy needed to. A 90 Orlyonok ekranoplan, flying one mistake above the sea. The A-90 Orlyonok was one of the most unusual military vehicles ever built, and few machines frightened their own engineers quite like this Soviet ground effect craft. Developed during the Cold War and entering limited service with the Soviet Navy in 1979, the Orlyonok was designed to exploit the ekranoplan principle, flying just meters above the sea surface to achieve high speed while avoiding radar detection. In theory, it combined the advantages of aircraft and ships. In reality, it operated in a narrow and unforgiving envelope where a single mistake could be fatal. The program emerged in the 1960s under the direction of Rostislav Alexeyev, a pioneer of ground effect vehicles. The Orlyonok was intended as a high-speed amphibious assault transport capable of carrying roughly 150 troops or 2 armored vehicles at speeds exceeding 400 kilometers per hour. Engineers quickly realized they were designing a machine that was neither fully an aircraft nor a ship, but subject to the dangers of both. Flight close to the water was the core risk. The Orlyonok relied on a cushion of compressed air between its wings and the sea surface. If altitude dropped too low, the craft risked striking waves at high speed. If it climbed too high, it lost the ground effect lift that made it efficient and controllable. Engineers feared that sudden wave patterns, wind gusts, or pilot error could cause catastrophic loss of control within seconds. Structural stress terrified designers. The Orlyonok's hull experienced constant pounding from wave impacts during takeoff and landing runs. In early trials, cracks developed in structural components, forcing redesigns and reinforcing fears that metal fatigue could lead to mid-mission failure. Unlike aircraft, the ekranoplan could not simply climb away from danger. Engine layout added another hazard. The Orlyonok used multiple turbofan engines mounted high on the fuselage to avoid water ingestion. During takeoff, these engines blasted air beneath the wings to generate lift, but failure of even one engine during this phase risked asymmetric thrust and immediate loss of stability. Engineers knew there was little margin for recovery so close to the surface. Navigation and survivability were also major concerns. Operating just above the sea left almost no reaction time for obstacles, enemy fire, or mechanical failure. A forced landing at speed would be unsurvivable. By the early 1980s, despite successful demonstrations, the Soviet Navy limited deployment. Engineers understood the truth. The Orlyonok was impressive, but it flew permanently on the edge of disaster. German K-Wagen supertank, a crew trapped inside a moving fortress. The German K-Wagen was one of the most extreme armored vehicles ever conceived, and it deeply unsettled the engineers tasked with turning it into reality. Designed during the final years of World War I, the K-Wagen was envisioned as a colossal breakthrough tank capable of crushing trench defenses and resisting all known anti-tank weapons. From the start, its sheer scale raised serious fears about whether such a machine could even function. Development began in 1917, as Germany sought a response to British and French heavy tanks. The K-Wagen was projected to weigh approximately 120 metric tons, dwarfing any tank of the era. Its armor thickness reached up to 40 millimeters, impressive for the time, and its armament included 4 77mm field guns mounted in side sponsons, along with multiple machine guns. Engineers immediately recognized that the vehicle was less a tank and more a mobile fortress. The crew requirements alone were alarming. Estimates ranged from 22 to over 25 men needed to operate the vehicle. Inside, conditions were expected to be suffocating. Ventilation systems were primitive, and engine heat, gun smoke, and exhaust gases would accumulate rapidly. Engineers feared that crew exhaustion or suffocation could disable the tank even without enemy fire. Mobility was the greatest concern. 2 large gasoline engines were planned to power the K-Wagen, but even combined, they struggled to move the immense mass. Calculated top speed was no more than 7 kilometers per hour. Engineers worried that the tank would be unable to maneuver effectively in broken terrain or retreat once committed. Mechanical failure under load was considered likely. Transport and deployment bordered on impractical. The K-Wagen had to be built in sections and assembled near the front. Rail transport was difficult, and bridges could not support its weight. Engineers knew that once deployed, recovery or repair would be nearly impossible. Most disturbing was survivability. While heavily armored, the K-Wagen's size made it an obvious target for artillery. A single mobility kill could trap the entire crew inside a burning, immobile structure. Engineers understood that, if penetrated, escape for dozens of men would be nearly impossible. By the war's end, only partially completed hulls existed. The K-Wagen never reached combat, but it left a clear lesson. Excessive size and protection had turned a tank into a potential mass grave, a reality its engineers quietly feared from the beginning. FV4005 Stage 2. Recoil that threatened to tear the vehicle apart. The FV4005 Stage 2 was one of the most extreme experiments ever conducted by British armored engineers, and it was a vehicle that frightened its creators with how close it came to self-destruction. Developed in the early 1950s during the Cold War, the FV4005 was Britain's attempt to counter heavy Soviet tanks such as the IS-3 by mounting an overwhelmingly powerful gun on a mobile platform. The result was a machine whose firepower exceeded what its chassis could safely endure. The project began in 1951 under the British Ministry of Supply. Engineers selected the 183mm L4 gun, the largest tank gun ever mounted on a tracked vehicle by Britain. The weapon was intended to fire Hesh rounds capable of destroying any known tank with a single hit. However, no existing British tank could realistically handle the gun's recoil forces. To save time and resources, designers mounted it on a modified Centurion Mark III chassis, a decision that immediately raised serious concerns. The gun required an enormous open-topped turret to accommodate its size and recoil mechanisms. This turret offered almost no protection, exposing the crew to artillery fragments, small arms fire, and even blast overpressure from nearby detonations. Engineers feared that the turret structure itself lacked the rigidity needed to safely absorb repeated firing stresses. Every shot transferred massive forces directly into the hull in suspension. Recoil testing was alarming. When the gun was fired, the entire vehicle lurched violently, with the suspension compressing to its limits. Engineers recorded significant strain on the turret ring, mounting points, and hull welds. There were fears that repeated firing could cause structural cracking or even catastrophic failure of the chassis. Unlike conventional tanks, the FV4005 could not safely fire on uneven ground, sharply limiting its tactical usefulness. Ammunition handling created further anxiety. Each 183mm round weighed over 70 kilograms and required 2 loaders to handle. Reload times were extremely long, leaving the vehicle vulnerable after every shot. Engineers knew that if the tank missed its first shot, survival against a moving enemy was doubtful. Mobility suffered as well. The added weight of the gun and turret stressed the Centurion's drivetrain and suspension beyond intended limits. Mechanical reliability declined, reinforcing fears that the vehicle would disable itself before enemy contact. By 1957, the project was abandoned. Engineers concluded that the FV4005's firepower had outgrown its platform. It remains a stark example of how pushing lethality too far can turn a weapon into a danger to its own crew. Soviet Object 279. Nuclear battlefield survivability at the cost of control. Object 279 was one of the most unconventional tanks ever designed, and it deeply unsettled Soviet engineers tasked with making it viable. Developed between 1957 and 1959 at the Kirov plant in Leningrad under the direction of Leonid Troyanov, Object 279 was designed for a battlefield shaped by nuclear weapons. Soviet military planners expected future wars to involve atomic detonations, radiation, extreme shock waves, and devastated terrain. The tank's purpose was to remain operational where conventional armored vehicles would be overturned, disabled, or destroyed, even if achieving this meant sacrificing traditional handling and reliability. The most striking feature was its hull. Instead of a traditional box shape, Object 279 used a flattened elliptical hull designed specifically to deflect blast waves from a nuclear detonation. Engineers calculated that this shape would reduce the force transferred into the vehicle and lower the risk of being flipped by an explosion. Armor thickness reached up to 269 millimeters in some areas, making the tank nearly immune to contemporary anti-tank weapons. While this protection impressed planners, engineers worried that the complex hull shape made manufacturing, internal layout, and maintenance far more difficult than on conventional designs. To further improve survivability, Object 279 used a 4-track suspension system rather than the standard 2. This distributed the tank's weight more evenly, significantly reducing ground pressure and allowing it to operate on snow, swamps, and soft soil where other heavy tanks would bog down. However, this solution introduced extreme mechanical complexity. Engineers feared that damage to even one track assembly could cripple the entire vehicle. Track synchronization, drivetrain stress, and battlefield repair were considered nearly impossible under combat conditions. Control was a constant concern during testing. The tank weighed approximately 60 metric tons, yet steering with 4 tracks proved unpredictable and mechanically demanding. Tight turns placed enormous strain on the transmission, and failures in coordination between track pairs could immobilize the vehicle instantly. Engineers noted that driver workload was exceptionally high, increasing the risk of operational mistakes under combat stress. Internal systems were designed for nuclear survival, including sealed compartments and overpressure protection against radiation and contaminants. While effective in theory, these features created cramped and uncomfortable conditions for the crew. Ventilation was limited, heat buildup was severe, and long-term crew endurance became a serious concern. Testing revealed the final problem. Object 279 had almost no tolerance for failure. A single mechanical issue could cascade into total immobilization. In 1960, Soviet leadership canceled the project, favoring simpler designs. Object 279 proved that surviving a nuclear battlefield meant little if the vehicle itself was barely controllable. M103, heavy tank, ammunition handling under extreme pressure. The M103, heavy tank, was the last heavy tank fielded by the United States, and it was a vehicle that caused serious concern among the engineers responsible for its design and testing. Developed in the early 1950s and entering service in 1957, the M103 was intended to counter Soviet heavy tanks such as the IS-3. While its firepower was formidable, the internal realities of operating the vehicle revealed dangerous flaws that made engineers uneasy, particularly in the area of ammunition handling. The M103 was armed with the 120mm M58 rifled gun, a powerful weapon capable of penetrating any known Soviet tank armor at long range. However, the size of the ammunition immediately created problems. Each round consisted of 2 separate components, the projectile and the propellant charge. This 2-piece system was necessary due to the sheer size and weight of the ammunition, but it placed enormous physical and cognitive strain on the crew. Inside the turret, space was extremely limited. 2 loaders were required to handle each shot, working in close quarters under combat conditions. Engineers feared that during sustained engagements, Fatigue would slow reload times dramatically. Under ideal conditions, reloads could take 15 to 20 seconds, but stress, heat, and vehicle movement could easily double that time. During this window, the tank was effectively defenseless. Ammunition stowage added another layer of danger. Rounds were stored around the turret interior, increasing the risk that a penetration or internal fire could ignite propellant charges. Engineers understood that, unlike smaller caliber ammunition, a 120mm propellant fire could rapidly fill the fighting compartment with flames and toxic gases. Crew survival in such an event was uncertain. The tank's weight worsened the situation. At approximately 65 metric tons, the M103 placed extreme strain on its drivetrain and suspension. Mechanical failures were common during testing, and breakdowns under combat conditions were expected. Engineers feared that a disabled M103 would trap its crew inside a vehicle loaded with massive ammunition under enemy fire. Operational use confirmed many concerns. Both U.S. Army and U.S. Marine Corps crews reported that the tank's firepower came at the cost of crew exhaustion and operational complexity. By the early 1960s, advances in main battle tank design made the heavy tank concept obsolete. The M103 demonstrated that overwhelming firepower could become a liability. Engineers learned that a gun too large for its crew could be as dangerous internally as any enemy weapon. Landkreuzer P.1000 Rata, a vehicle that could not be protected. The Landkreuzer P.1000 Rata was one of the most extreme military vehicle concepts ever proposed, and it terrified German engineers precisely because it could never be protected in combat. Conceived in Nazi Germany during World War II, the Rata was envisioned as a 1,000-ton land battleship that would dominate any battlefield through sheer size and firepower. From the moment the concept was examined seriously, engineers understood it was fundamentally unviable, not because it lacked power, but because its sheer scale made survival impossible. The design emerged around 1942, heavily influenced by Adolf Hitler's fascination with oversized wonder weapons. The proposed vehicle would weigh approximately 1,000 metric tons and measure more than 35 meters in length, with a width exceeding 14 meters. Its primary armament was to be a twin 280mm naval gun turret derived from Kriegsmarine battleships, supported by multiple secondary cannons and anti-aircraft weapons. On paper, the Rata could destroy fortifications and enemy armor at extreme ranges. In reality, its size created insurmountable engineering nightmares. Protection was the central issue. Engineers quickly calculated that armor thick enough to resist heavy artillery shells or aerial bombs would add hundreds of additional tons, pushing the vehicle far beyond any practical limit. Even with relatively thinner armor, the Rata would remain an enormous, slow-moving target visible from kilometers away. Its silhouette alone guaranteed detection, making concealment or surprise completely impossible. Mobility concerns were equally severe. No engine available to Germany could realistically move such mass across real terrain. Proposed solutions involved multiple marine diesel engines, similar to those used in submarines, but even these offered limited speed and extreme mechanical complexity. Ground pressure would crush roads, collapse bridges, and cause the vehicle to sink into soft ground. Engineers knew the Rata would be restricted to a few prepared routes, making it predictable and easy to target. Air power sealed the project's fate. Engineers openly feared Allied bombers, recognizing that no amount of onboard anti-aircraft weapons could defend a vehicle of that size from coordinated air attacks. The Rata would be a priority target, and a single well-placed armor-piercing bomb could disable or destroy it. Once immobilized, it would become an immovable target rather than a weapon. Logistics made the concept even worse. Fuel consumption would be enormous, maintenance would require shipyard-level infrastructure, and recovery after damage would be impossible. By 1943, as Germany's strategic situation worsened, the project was quietly abandoned. The Landkreuzer P.1000 Rata stands as a warning etched in steel and paper. Its engineers understood a simple truth. A vehicle that cannot be protected is not a superweapon, but a liability waiting to be destroyed. M551 Infantry, fighting vehicle. Troops seated above their own fuel tank. The BMP-1 was the world's first true infantry fighting vehicle, and when it entered Soviet service in 1966, it fundamentally changed mechanized warfare. Yet, behind its revolutionary concept was a design choice that deeply worried its own engineers. Infantry troops were seated directly above large internal fuel tanks. This decision, driven by space and weight constraints, created a vehicle that exposed its occupants to extreme danger even before enemy fire was considered. The BMP-1 was developed in the early 1960s by the Chelyabinsk tractor plant to transport infantry alongside tanks while allowing them to fight from inside the vehicle. To keep the silhouette low and weight under 14 tons, engineers packed the internal layout tightly. Fuel tanks were integrated into the floor and rear sections of the troop compartment, with soldiers sitting and standing directly above and beside them. Engineers immediately recognized the risk, but alternative layouts would have required a larger, heavier vehicle. In combat, this configuration was terrifying. Any penetration of the hull, even by small-caliber weapons or shell fragments, risked rupturing fuel tanks beneath the troops. Engineers understood that burning fuel inside the troop compartment would spread rapidly, leaving little chance for escape. Unlike external fuel tanks that could burn away from the crew, the BMP-1's fuel was effectively inside the passenger space. The rear exit design worsened the danger. Troops exited through two rear doors that also doubled as auxiliary fuel tanks. Engineers knew that infantry dismounting under fire were literally stepping past containers of fuel. If those doors were hit while troops were exiting, ignition could occur at the worst possible moment. Combat experience confirmed these fears. During conflicts in the Middle East and Afghanistan, BMP-1s were frequently destroyed by anti-tank weapons, heavy machine guns, and mines. Penetrations often resulted in catastrophic fires, killing passengers before they could escape. Engineers reviewing damage reports saw that survivability for dismounted troops was far lower than anticipated. Additional problems compounded the risk. The low roofline forced soldiers to sit hunched over, slowing evacuation. Ammunition for the 73mm gun was stored nearby, increasing the chance of secondary explosions. Engineers understood that once a BMP-1 was hit, internal fire spread faster than in most armored vehicles. Despite later upgrades and improved variants, the core layout remained dangerous. The BMP-1 terrified its engineers because it achieved innovation by sacrificing internal safety. It proved that transporting infantry inside armor means little if that armor turns into a burning fuel container the moment it is struck. Experimental nuclear-powered tank, Project TV-8, radiation inside the crew compartment. Project TV-8 was one of the most radical armored vehicle concepts ever proposed by the United States, and it frightened engineers not because of enemy weapons, but because of what it carried inside. Developed in the mid-1950s by Chrysler Defense under U.S. Army sponsorship, the TV-8 envisioned a nuclear-powered tank in which the crew, engine, and reactor were all housed inside a single massive turret. From the beginning, engineers understood they were designing a vehicle where survival depended entirely on flawless containment and systems that could not afford to fail. The concept emerged during the height of Cold War nuclear optimism. Military planners believed nuclear power could give armored vehicles virtually unlimited operational range, while eliminating dependence on vulnerable fuel supply lines. The TV-8 design featured a large spherical turret weighing more than 25 tons, containing a compact nuclear reactor that would generate electricity for electric drive motors. The hull beneath was relatively small and lightly armored, serving primarily as a mobile platform for the turret rather than a traditional fighting compartment. Radiation exposure was the most immediate and persistent concern. Engineers calculated that shielding thick enough to protect the crew from neutron and gamma radiation would add enormous weight and consume valuable internal volume. Even with extensive shielding, long-term exposure inside the enclosed turret raised serious health risks. Designers worried about cumulative radiation doses during prolonged deployments, recognizing that crews could suffer dangerous exposure levels without any visible warning signs. Accident scenarios were even more alarming. Engineers examined the consequences of a mobility kill, rollover, or direct penetration by enemy fire. Any damage to the reactor or its shielding risked releasing radiation directly into the crew compartment. Unlike fuel fires or ammunition explosions, radiation contamination could not be outrun or quickly escaped. Even abandoning the vehicle might not save the crew if exposure occurred inside the turret. Heat management added another layer of danger. The reactor produced continuous thermal output, requiring complex cooling systems to function flawlessly under combat conditions. Engineers feared that damage to cooling components could cause overheating or even partial meltdown inside the turret. In such a confined space, there would be no effective emergency response for the crew. Maintenance concerns ultimately doomed the project. Reactor servicing would require specialized facilities, nuclear-trained personnel, and strict safety procedures. Battlefield repairs were impossible, and even routine access raised contamination risks. By 1957, the U.S. Army quietly abandoned Project VIII. Engineers concluded that nuclear power's promise of endurance was meaningless if the tank itself endangered its own crew.